Okay. So we just start. So our next module is particularly interesting, fascinating, the Dutch history. All of you know, I told you yesterday, it's perhaps the greatest thing where under me gameplay actually rubber meets the road, society benefits, beneficial things, beautiful theory. So we learn about that. Our next video classes out of the way. So our next speaker is faculty at is incredible and whatever.
Thank you, Sushmita, and the organizers for inviting me. I plan to have like this classroom lecture, so please feel free to stop me and ask me. On a broader context, I feel that this mechanism design can be broadly categorized into two parts. Where, so let me write. So, or in general game theory also. So, on one part what you have seen till now mostly in the school is each player has a utility function. So, players exactly know the his or her utility of every outcome, right. So, players know her utility, which is a real number. Okay. So, this under this setting we have learned auctions and various kind of games on graphs, public goods games and various other things. Typical most kind of game theory and mechanism design is on this. But there are other kind of game theory and mechanism design where players do not know these numbers, which are which is more sometimes or arguably more applicable in systems involving human being. For example, suppose there are two flavors of ice cream, vanilla and chocolate. I know I like chocolate than vanilla, but okay, how much, what is my utility, that I do not feel I know. So, here players have a preference order, let me write preference over the outcomes. But just preference. Now, what do you mean by preference? Now, here many things can come up. So, what we will mostly deal with in this lecture is players have a ranking over the outcomes. So, this is my top choice, I like Salman Khan most and Sunil Shetty least, this kind of thing. So, and this is by far the most studied model of preferences in algorithmic game theory as far as I have seen. But there are other models. For example, an extension of this is what is called weak order. Weak order is like this. So, no, it is like there are some set of outcomes which are equally likely, and these are the best set of outcomes for me, then followed by another set of outcomes and so on, right. So, these are indifference classes. So, I think if the number of outcomes becomes large, this is more closer to how human beings think than this sort of thing. Another is, say, I do not know, top K. We have done Google search, all matters is the first page, top 10 results. Although that, so again, so these are more whenever human being comes into picture, they are the players, their preferences matter. Because of cognitive load and maybe vastu reason, and I do not know for some other reason, it takes load. If you have say 100 outcomes, you can't rank 100 outcomes, right. So, these are more closer to ground reality. Yeah, sorry, weak order is the set of outcomes is partitioned into indifference classes, and I just rank that indifference classes. So, for example, I have say yeah. So, a nice example of weak order is grading system. All the students who get say more than 90 are EX grade, right. So, they are the sort of best. So, if we only look at grade, so EX grader is the best performer, followed by A grader and so on. So this partitions the outcomes into indifference classes. These are called indifference classes because among these classes all outcomes are same for me. I am indifferent to different outcomes within one class, but I prefer every outcome in O1 over any outcome in O2. And last but not the least is what is called approvals. In many things, many practical things, for example, say faculty hiring, being part of a faculty in IIT Kharagpur, I know at the end it boils down to this. You can have many discussions and these things, भाई इसको लेना है कि नहीं लेना है? So tell me, do you approve or not? So here the preferences are subsets. So each player simply saying I think this I like this set of alternatives and nothing else. So you see, so these are much weaker models. So for whereas these here players exactly know what is the exact utility of any outcome, and this makes sense where monetary transactions is involved. If the outcomes involve money, that makes sense. I prefer 100 rupees less than 100.0001, which makes sense, but where monetary transactions are not allowed for various reasons, maybe because of law or maybe because of various reasons. For example, in faculty hiring, I cannot have monetary transaction in say voting, in say marriage and various other things. Monetary transaction is not allowed, or that is not the main goal. So there once this objective thing goes away, things become subjective. This kind of preferences makes more and more sense. So I will give a broad overview of some part of mechanism design or game theory which deals with basically ranking, but there is a vast amount of literature which deals with other kind of preferences also. Okay, question?
In this approvals, we have only one subset or many such subsets?
So all these things is that each player has a subset.
Okay.
So these are modeling the utilities, you can say, or player's preference. So when I say ranking, that means each player has a ranking. When I say weak order, each player has a weak order over the possible set of outcomes. Here each player says which are the approved set of candidates or which set of alternatives I think is good.
So, like, can we think of a hierarchic order only, but it is S greater than O minus.
Exactly. So it's like, you can model approvals as top K ranking also. So these are more powerful, more richer models, but as I said, depending on human cognitive ability and various other things, many things, for example, if you see in faculty hiring or in many cases, at the end what matters is that or any hiring process, is that guy hired or not, say PhD selection, is that guy hired or not, that's the matter, and there some often the question boils down to can that guy will be able to do a PhD, will be able to do a good research, that's the end question, and the answer is yes or no. So in those sort of applications, these approvals preferences makes more sense. Am I making sense? Okay. Okay, so let me erase this and then delve into this sort of ranking, but this is the big picture. So I will just only present something on ranking, and maybe tomorrow something on other things if I get time. So as Shushmita rightly pointed out, among the most successful applications of game theory in a human life is matching. So let me introduce the problem. So the problem is stable matching. So what is stable matching? We have a set of men and women, their numbers are same, and each man has a preference over a ranking over all the women, and each woman has a ranking over all the men. Typical applications are any matrimonial site, shadi.com or any such thing. But here again you see, do you see that even in say in any real world application, say shadi.com or whatever, it is impossible for any man to go over all women listed there and have a ranking. You see, so then here again it makes sense to kind of, I don't know, top K or what are the right model, but this model where we assume that every man has a complete ranking over all omens and same as omens is definitely not scalable. It does not seem scalable to me, and hence this becomes new research agendas. Okay, so what is the right model and what are the research questions? But let me, with this assumption, let me show you the theory, and it is a beautiful theory. I have seen theories around matching, sometimes very beautiful, very rich. So let us introduce this theory. So let me write each man has a, let me write ranking and what I am looking for matching which is stable. Now let us understand what does stability mean in today's context where divorce rate is going high. Why divorce rate is going high? Because there is a man and there is a woman who like each other than their current partners. common problem with married people, you will know. So let us try to get a matching where such pairs do not exist, assuming people's preference always like that till they die. Okay. So what do we want to avoid? Want to avoid. So let M be a matching a matching is called perfect when all men and women are matched. So let M be a perfect matching when this is a bad matching when such a pair exists. So such a pair is a bad pair if so by this notation I denote the ranking of man M. Okay. So this man prefers W, this woman, over his matched partner, which I denote by M of M. M is the matching. Okay, is this notation clear? Greater than suffix M means M's ranking, and also that woman prefers this man M under compared to her partner. Okay, so these are the bad configurations, and these configurations we want to avoid, and these configurations are called blocking pair. So this bad is called blocking pair. And condition, good, very important. If both of the following holds, दोनों कंडीशन होगा तभी तो डिवोर्स होगा ना. Okay, makes sense. So our goal, so the question, okay, so let me write. So a matching which does not have any blocking pair is called a stable matching, which is stable. So what is a stable matching? So perfect matching with no blocking pair. Okay. So this is a classical problem, and a seminal work by Gale and Shapley started this field, and because of this work primarily they got Nobel Prize, because this is a problem which impacts society directly. And it has, by the way, other than this there are many other applications also. For example, one side could be hospitals and the other side could be doctors, and that is an extension of this, and each hospital needs certain amount of doctors, but hospitals has a preference over doctors and doctors also has preference over hospitals. Now again think of what is the right notion of stability, it will be a cousin of these conditions. Under that notion of stability, can you find a stable matching doctors to hospitals, and that this algorithm is actually used in US and many European countries to assign doctors to hospitals. Okay, so now let us see an algorithm for stable matching. A priori, I think it is not even clear why for an arbitrary instance there will indeed exist a stable matching. Yeah. So, what we will see an algorithm which will find a stable matching. So, it will prove not only existence, but how to find it efficiently, and that is the celebrated Gale-Shapley algorithm. And this is the I don't know, this is a very practical algorithm we see in society. So, okay, so we will abbreviate it as GS. So, let me first verbally tell you what is the algorithm, and then I will write the pseudocode. So, as I said, this is seen in all societies from I don't know, time immemorial, that men proposes and woman either accepts or rejects, and that goes on, right. That is the algorithm. So, whenever initially all men and women are unmatched, any man who is not matched, to any woman, prefers or proposes which woman? That woman who is the highest preferred, right, as he said. Now, that woman either she is already matched with somebody else or unmatched. Now, everyone prefers to have some partner than remaining unmatched. So, the woman who has just received a proposal, if she is unmatched, she will accept the proposal. On the other hand, if she is already matched, she has a choice. So, she accepts the better of the two. Okay. So, and that is the algorithm. So, these things go on. It is not a priori clear why this will lead to a matching, forget about why it is stable matching, but this is the algorithm. So, let me write the algorithm. So, while M is a perfect matching, so initially M is empty, no one is matched, and the algorithm terminates when M is a perfect matching, everybody is matched. So, let A so I pick any unmatched man M. Yes, is not a perfect matching. Correct. Not a perfect matching. So, that man proposes to the most preferred woman in his list among the women who has not already rejected him. So, maybe some woman has already rejected him, then the first woman, most preferred woman has already rejected, then he will propose to the next woman and so on. Life goes on, right? Let me woman, let's call, give her a name, say W. Then W has two choices. If W is unmatched in M, if W is unmatched, then W accepts his proposal, which is mathematically equivalent to say that M comma W becomes partners and part of the matching. Else if so now there are two cases. If W is already matched, either W prefers M over her partner in this matching, then W get rid of M W and matched with M. I think that is it, because in the other case W prefers M W over M, then W simply rejects M. So, the current matching does not change. So, this continues. Okay. Now, it is kind of weird, it is not clear that can we have a case where M is not a perfect matching yet, but this man M has exhausted his list of all women. This something seems incomplete in this algorithm, right. So, can it happen that I have entered this while loop because M is not a perfect matching and I have picked a man M who is unmatched, and this next step is saying that asking M to propose to his most preferred man woman whom he has proposed, who has not rejected him. But can it happen that M is already rejected by all women in this world? No. Okay. Why? Both are equal. Okay.
Like both the sets are equal, and if all of them can't be married at the same time, because there are only n minus 1 men and n women, so one woman will be left at least. Because this rejection
yes, so that's not perfect.
Already,
so this is not perfect matching. So at least one woman is left. So
like he will be matched.
Who will be matched?
So it will not happen that he won't be matched.
He means M.
MM, yes.
No, M is so why means that
Because
that
there
is
is
the
still
question.
a woman left, so he will be matched to her because she does not have anyone tied with her.
Why?
Because there are only n minus 1 men here and there are n women here.
Correct. That's true. But maybe M has already proposed to her before.
No, but then she would not have rejected him, right?
Yeah. So what is the main point? Okay, so so there are many things. Your answer is correct. But can you hit the bullseye? What is the main point
Like
in this proof?
For her to reject him, she should have been tied to someone better than him.
Yeah. Okay. Anyone else? What's the crux of the any theorem? Sorry. Yeah. So we don't need that big hammer. There is a. Have you heard of the human or mental model called man with a hammer? Once you have a hammer, every problem looks like a nail. You don't need much easier. Yeah. I think the main point here is that a woman once receives a proposal is never unmatched throughout the algorithm. So, let me write down. It is not true for men. A man can, throughout the run of the algorithm, it can initially everyone is unmatched, it can get matched, then it can again become unmatched, it can again become matched, it can happen many times for men, but for women it cannot happen. She can change partner, but she will always remain matched. Okay, is this everyone agree with me? Please feel free to disagree. For this basic reason that many times I write wrong thing, and this is recorded. So, is this fine? Now, if this M is not a perfect matching, that means there exists a woman who is not matched. That means that woman has not got any proposal yet. That means this particular M must not have proposed that woman. Okay, so this algorithm makes sense now. I can't have a step which does not make sense. This algorithm makes sense because of that observation. So, this okay, and so the algorithm terminates with a perfect matching, because this algorithm makes sense. Only way this can terminate is when M is a perfect matching. Why it is stable?
Because the woman has a choice to get a better man. So
Yeah. So, let me write. So, here, so corollary, GS terminates with a perfect matching. Beautiful chalks and boards. I really enjoy writing there. So, at the output I have a perfect matching. Why it is stable? Short. Sorry? Yeah.
Let's say that it's not stable, then it must have a
Blocking pair, correct, yeah.
So then, say W is preferred, W prefers some other man over her as partner.
Yeah.
So when that man will propose her, she will just dissolve this. Union.
So let us call it M, and this is W, and I need to show that M, if M and W are not matched, they are not blocking pair. That's what you are showing, right? So, and your argument is for this to be a blocking pair, W must prefer M over this guy, correct? Yeah, M over this guy, and then continue, please.
So when M will propose to W.
Yes,
W will dissolve.
but maybe M never proposed to W.
no, but if because M proposes to all the women in his order.
No, not necessarily. No, it's not. Why M should propose all the women in his order?
Until he is getting
He would have stopped proposing before W only when he would have been matched to his most preferred woman. So the second condition would not have.
Correct. So can you finish the proof? Sorry. Yeah. So then, you two have said two parts of the proof.
Yeah.
So let me consolidate. So I need. So suppose this is the perfect matching I have. I need to show that there cannot be any blocking pair. So let's take any MW pair If they are already matched, then they are already happily married. Otherwise, if they are not matched, then I claim they are not blocking pair. So, there are two cases. So, for them to be blocking pair, both should be true, that in W's preference M should be over MW, and in M's preference W should be over MME. Now, if both are true, assuming both are true, let us find a contradiction. So, if both are true, then M is matched to some woman who is ranked lesser than W. This hence M must have proposed to W, but then and whenever W changes her partner, any woman changes her partner, only gets better partner. So, this because M proposed to W, W's partner must be better than, at the end of the algorithm, better than M, but how can this be? This contradicts this. Let me again say, using this, W is preferred over partner of M, that means M must have proposed to W, and W eventually is not married with M, that means W's partner should be better than M, but then that contradicts this. So, this is a stable matching. Okay, so good. So, this is a stable matching. It's theorem. What is the number of proposals? So, so let us for making our life simple, let us say the complexity of the algorithm is the number of proposals that a man makes. This way we do not need to get our hand dirty thinking about what data structure is used, so that we can do it efficiently in less time. Although that is a very important question, this is a very practical question, practical problem, and very important question. So, what is the number of proposals in worst case? N square, right. So, because every man can propose to at most n women, there are n men. So, number of proposals is at most n square. Good. Now, you see that there is a fancy term called non-determinism. No, there is certain amount of this algorithm is under specified. It seems that if I implement this algorithm and you implement this algorithm, the programmer has a choice of picking M. Under specified, sorry, not non-determinism. This algorithm is under specified. That the algorithm does not specify which unmatched man you are picking. So, a priori it seems that various implementations of this algorithm, same algorithm, will output various different matchings, because that can depend on which man you are picking here. So, here is another beautiful and amazing result, is that it does not matter which man you pick, the resulting matching is same. That is one which we will prove. Second, it does not matter which man you are picking here, the number of proposals, all I know is at most n square, but the number of proposals also are exactly same. Not only the output is same, the number of proposals are also exactly same, irrespective of which man you are picking. Amazing, no? So, let us prove these two things. Let me erase this. And this is just the tip of iceberg. You know, in 1989 or something around that, there was a green book which is around 200 pages, which lists lots of such structures, and one would imagine that, you know, it has so much explored that it's almost done. This is saturated, this area, and then so much work has followed. Then around 2007-8, Manlove wrote another book around fatter book, which focuses on development only after that green book. And after that book also there is so much development and it's still going on. So if you look at any premier conferences in both theoretical computer science and AI, there will be lots of papers on matching, which are in some sense stable matchings and these various incarnations. As I said, you know, depending on application, one is how you model the preferences or rankings, preferences, and so on. Okay, so let me write down this big claim, which we will prove herein. Okay, is this obvious to anyone?
So the second point, like say if we have the men and women blocks, and say like we have a proper ranking of men, proper ranking of women, and all of them have the same ranking. So the first man gets matched with first woman, second man with second woman. So in this in n proposals we are done with the stable matching. But now if I start with the last one and I compare him with the first one, so he gets matched with her. But later now if I start with the first man who proposes to this first woman, then she rejects the last man.
Yes, I think.
So then here we have more than n, right?
So it seems this is wrong. This one, second part, right?
Yes.
Maybe, I don't know. Let's see. So either then there will be some bug in the proof. By the way, here men are proposing, but now men and women are same. So you can think of the same algorithm where the role of men and women are reversed. So this is sometimes called men proposing Gale-Shapley algorithm. The other one where women are proposing and men are deciding, that is called women proposing algorithm. Okay, good. So for this, actually I will show another theorem from which it follows. So for that, let me define a notation. Let me define a function which from set of men to set of women, and h of a is h of m men is that woman such that that W is the best means most preferred, just being lazy, best partner of M under any stable matching. So, you see in a instance there could be multiple stable matchings, solution may not be unique like any typical optimization problems. The optimal solution here, a solution is a stable matching, need not be unique. So, a man or woman vice versa. So, a man can get various partners in various stable matchings. So, H of M is that woman who is the best partner among all stable matchings that the man can possibly get. Okay, is this function clear? Yeah, why is in the set? This is not set. Yeah, W. Yeah, this is not a set, correct. A to B, sorry, yeah, thank you. Horrible way of writing this anyway. Yeah. Okay. Now, what is another amazing thing is that you take A and B, and here are the set of men. Each man you assign it to H of M. I claim that this is a stable matching. It is a priori not clear whether why it is a matching, right? Is it clear why it is a matching?
But we are saying that H of M equal to W, where W is the best partner of M under any stable matching.
In a stable matching, correct. So
this
why there can, so maybe there exists one stable matching where my partner is Aishwarya Rai, and there is another stable matching where your partner is also Aishwarya Rai, then both of our H is Aishwarya Rai, right? Correct, yeah, M1 not equal to M2, but H this function. So, what this basically says, this is a bijective function. Why this is a bijective function, it is not clear, and more why it is a stable matching. Then first matching is not clear, matching नहीं हो रहा है, stable matching, शादी नहीं हो रहा है क्या stable. Okay. Yeah.
Is this function even surjective?
Yes, yes. So, I will prove that this is a matching and it is a stable matching which will resolve everything. A priori it is not clear, because this set size is same, surjectivity, injectivity, bijectivity all are same, both are cardinality n. So, this is a fast non-trivial interesting thing, let us prove it. And moreover, yeah, this matching is output by this algorithm. This algorithm outputs this matching. So, main ke liye balle balle. So, they are getting their best partner. So, that is why this version, this matching which is output by this algorithm is called main optimal stable matching, because every man is getting matched to the best possible partner he can hope to get matched in any stable matching.
If we reverse the roles, then
If you everything what I say throughout the lectures, reverse, swap men and women, everything remains same.
because when you are saying it is men optimal, it seems like it is not women optimal.
Definitely.
So, like, what is the case where it is not like? What is the case where it is not women optimal? Because here women are making choice of going to a better man every step.
Yes, yes. This world looks that it's for women. It's not. You know, it is men optimal. That's why this is.
Best possible.
Sorry?
In a theoretical sense, best possible.
This is the
or
best possible.
Will you just run it like a lot of times and then choose the best?
No, nothing like that. What I say is that you just run it. Nothing like, there is no randomness here. And because of this theorem, the output is same always. Okay, so let's prove it. I think then.
For this profile, of course, you have a profile, right? So if you change the orders of the men, the reference of the men, reference of the woman, then a different matching may show up. And yeah, so men optimal and women optimal may be the same when you have exactly one stable matching. So if you have a unique stable matching, then whether you propose in the men way or the women way,
Oh, you are leaking my secrets, Okay, so let me erase this thing. Yeah.
Good to even say that it's also called deferred acceptance.
Yes, yes, correct. Thank you. This is also popularly called deferred acceptance algorithm, DA algorithm. Yeah, thank you. This is a popular name. Yes, yes. I think the motivation from being from the woman's point of view. They got the proposal, they are not as soon as getting the proposal accepting it. It's like okay, keeping it. It's like a job proposal. Got let's see, अगर better मिला तो इसको ना कर देंगे. So acceptance is deferred at the end. So that's maybe the name deferred acceptance. Okay. Okay, so what was the notation? Yeah. So Ri so let's take a run of the algorithm. Fix anything and take a run of the algorithm and we'll see. With respect to that particular run, I am defining few notation which will prove all those things. So Ri is those set of pairs m comma w where w rejects m in the first I iterations, in some iteration from 1 to I. So R0 is empty set, and suppose the algorithm runs for capital T iterations. So let us define R equal to union Ri. So this is the set of all rejections, this R. What I show is that there is no stable matching where any pair in this R can get matched. So theorem. There is no stable matching with stable matching M with M comma W in M for any M comma W in R. Capital T is the number of iterations. So I have run this algorithm once, irrespective of choice. Do whatever you choose, you just run it once, and based on that run of the algorithm, you define those things which are basically you are keep tracking of rejections. What are those rejections? And what this theorem says is that if a man gets rejected by a woman W, then in no stable matching M can be matched with W. If I showed this, then it shows that this algorithm, in this algorithm, every man is getting matched to the woman which is best possible among all stable matchings. Yeah. So Ri are the set of all rejection pairs which has happened till iteration I.
So it can be maximum I minus 1 for I iterations.
I iteration, I.
Like first time she will get paired and then she will start rejecting if it is the best one.
No,
Like
no,
I am in a
don't look at from a particular woman's perspective.
Okay.
So for example, even R1 is empty set also. R0 is empty set, R1 is also empty set, because in the first iteration everyone is unmatched. A man proposes a woman, gets matched. Okay, so even R1 is also empty set. Do you see? R0, R1, they are empty set. But in the second iteration, maybe another man proposes that matched woman. That there will be one rejection. That part, that rejected pair, you put, that will be R2.
And in that same iteration, then he will be.
Forget, don't look at acceptance. Rejections. RIs are rejections.
I'm asking in this iteration.
Yeah.
So this in each iteration, at least one pair is made, right?
Yeah. Okay, and what I am saying is that, you know, you look, then R is the set of all rejections across the run of the algorithm. And what I am saying is that these rejected pairs can never be paired in any stable matching, not only this stable matching, not any, there does not exist any stable matching where any rejected pair can get paired. Yeah. No, no, no. From this I will prove that.
So then do we not need one more, like Ri is, we haven't differentiated between, like among
Yes,
iterations
yes,
of-
that's what I am saying. So these are defined with respect to one run of the algorithm. It's like you run this algorithm once. Okay? It's not with respect to this pseudocode. It is defined with respect to one execution of the algorithm. Very good point. You execute it once, see the trace. With respect to that execution, you define these quantities.
So it should be like R with some superscript, something else. Like there are different R's. At like now, without assuming that here.
We are not, we will prove this.
Yeah. So,
So
now
this
there
is
will
with
be-
respect to one execution. So this is with respect to an execution of DA. For different executions I will have different things, but you execute DA once and with respect to that you define these quantities.
So and secondly, like the theorem that we have written, there is no stable matching M where some pair in R is matched.
Matched, correct.
So this is among all stable matchings or
Among all stable matchings.
okay,
Among all stable matchings of the instance.
not like
All stable matchings. All possible stable matchings of the instance. Not only the possible outcomes, among all possible stable matchings.
But we just said there is only one stable matching. We'll prove that later.
No, I am proving this.
Yeah, but that's what I'm saying.
Sorry, what did I say?
I'm saying there's only one stable matching. The spoiler.
Yes, yes, what he
No,
said.
that is
That
what
we have
Ah.
to prove.
No, no, so that is not.
Forget him, ये बॉम्बे वाले. Forget him. Erase that.
Okay, but then I'm confused. Like you're saying the output is same.
First of all, you forget him. Then you ask me.
The output is same.
This I will prove.
Irrespective of- This will come later.
This I will prove.
Yeah, but
I am
I'm
proving
asking
this.
what that theorem means.
Oh, this theorem means that irrespective of which man you pick here, the output will be same. And that is the best for all men simultaneously.
Among all stable matches.
Among all stable matchings, correct, thank you. Yeah.
For one instance.
Yes, everything is for one instance. Instance means every man you have written the rankings, every woman you have written the ranking. That is the input to the problem, input to this computational problem. In any typical computational problem, there are very many optimal solutions. Here also, for an input instance which consists of n rankings for men, n rankings for women. For this instance, for any instance, I can have many stable matchings. And what I claim is that this algorithm outputs the stable matching which is best from men's perspective among all possible stable matchings.
Does the theorem imply that
No, I have not proved the theorem yet. Yeah.
I'm just asking, does the theorem imply that there's only one stable matching?
Oh, again, you got the spoil. No, forget it. If you have to ask one stable, no, if you say one stable matching, they say in T to him.
Sir, but that, okay, sorry, but the thing is still unclear. Like, you are saying the same irrespective of unmatched mat picked. So, in one iteration, we have a lot of choices, right? So, out of those choices, if we pick any, suppose any arbitrary man, then the whole matching will be same, right? Like, per iteration.
At the output.
Per out.
So it's like you pick as per your rule. You pick your unmatchment as per your rule. Run this algorithm. You have some rule. Got an output. I from here so that you cannot see, pick as per my choice. Got an matching. Our output should be same. Okay, maybe let's take some time and then let's come back here. I think then many things will be clear. So here, what I have done, I have run this algorithm once. Now with respect to that run of the algorithm, I know in which iteration which man has proposed to whom, which in each iteration which woman has rejected whom. So all those things with respect to this, I have defined these sets, these RIs. Right? These are with respect to the execution of an algorithm, not with the pseudocode. Run the algorithm once. R is the set of all rejections, rejected pairs. There is no stable matching for the instance. Everything is for an instance where M and W are matched. Right?
So one quick question. So even for two different executions, T might differ.
Yes, very good. We will see. T will not differ actually. We will prove it.
Okay.
Uh,
So suppose I go over M1 in a different order, then also
T will be same. But yeah, it seems T can differ, RIs can definitely differ, many things can differ. So that is why I am saying let us define these quantities with respect to this. Okay, is this now making sense? Sorry.
No, like R is with respect to one run of the algorithm.
Yes, T is also that.
So then this theorem should be at either one of the two. Like there is no stable matching with any R or this R. Like
Say these are.
so you are picking some R arbitrarily.
I have picked one run arbitrarily. I have picked one run of the algorithm arbitrarily and proving some theorem with respect to that run of the algorithm, because everything is with respect to that run of the algorithm. Okay, good. So let us prove it. And proof is easy. We will prove by induction on I. So induction on I. So I equal to 0 and 1, nothing to prove. That is the beauty of induction. Yeah, I don't have nothing to, I have nothing to prove. So let us assume for I, and so let us assume this theorem till I, and let us prove for R I plus 1, right. So let me write, assume for R I and to prove for R I plus 1, right, typical induction. Now here I can have two cases. In the I plus 1th iteration, there is no rejection, right. If at the I plus 1th iteration there is no rejection, if no rejection in I plus 1th iteration, then what is the relationship between R I plus 1 and R I? Same. Then by induction hypothesis I have this result. So I only need to prove it for the other case when at I plus 1th iteration there is a rejection. In every iteration there can be at most one rejection, दो rejection नहीं होगा, at most one rejection. So, let me erase this. So, let us see the scenario. So, say M in A proposes W in B in I plus 1th iteration, and W rejects maybe M prime in A, right. Some man M proposes a woman W and W rejects M prime, which could be either M or the previously matched partner of W, M prime, either M or already matched partner of W. So, what is R I plus 1 then? R I union M prime W. So, again by induction hypothesis I have this result for all pairs in R I. I only have to prove this result for this pair. What I need to show that there is no stable matching where M prime is matched with W, that is what I need to show. So, let us show it.
Excuse me.
Yeah.
So there can be two types of rejections, right? If none of the conditions are satisfied, then also you get
Yeah, two kinds of rejections. So, depending on that M prime could be either M or the currently matched partner of W, both the proof same. So, no need to bifurcate the cases. So, now let us see what information do we have. We know, okay. So, it is a proof by contradiction. So, let us assume there is a matching stable matching where M prime and W is matched. So, for contradiction, suppose there exists a stable matching say M prime which contains M prime W. Right? There is a stable matching where M prime and W are matched. I will contradict this. Okay. So, let us look at W's preference. W has rejected M prime, right? And the currently matched partner of W, let us call it M double prime, just I plus 1th iteration. At I plus 1th iteration, W has rejected M prime and she is with M double prime. This is the partner of W at the end of I plus 1th iteration. You do not know, maybe M double prime was the original partner.
Why will she reject M dash?
if W is rejecting someone at this current state, she will switch to M, right?
That maybe she is rejecting M also, M.
But that should be
And
after
sticking
the
with-
iteration. That should be I plus 2th iteration.
There won't be any reason for her to reject, right?
M prime can be anything, either M or the previous matched person.
Yes, I think yeah.
Yeah, it's like that.
So, here she W is matched with some guy and M proposes to her. Now she rejects either this guy or M, right. So the rejected guy I am calling it M prime. M prime could be this guy or M also, and M double prime is the partner after that rejection hangama ho gaya to kiske साथ है, that is M double prime. So M double prime can also be M. So M double prime is either M or the original partner, and this is the other guy, rejected guy, right. Now can you give me a blocking pair? The blocking pair is on the board. M double prime W is a blocking pair to which matching? M prime. Can you elaborate why? The answer is correct. That is for W. The for blocking pair, for W it is clear that if there is a stable matching where M prime is matched with W, W prefers M double prime more than M. That part of the blocking pair constraint is fine, but I have another constraint. This M prime, M double prime also, yeah, should correct, exactly. So here is where we are using induction hypothesis. Let us look at the preference profile of, let us denote it by M double prime. Preference profile of preference ranking of M double prime. Say some, this is W1, then W2. यहाँ पे कहाँ पे somewhere W comes, right. Now do you see that, you know, at this iteration after I plus 1th iteration here M double prime and W is matched, right. After I plus 1 the M double prime and W is matched. So M double prime has already proposed this omen and got rejected. That is why M double prime comma W1, M double prime comma W2, all this belongs to Ri. And by induction hypothesis I have that there is no stable matching where M double prime can be matched with W1, M double prime matched with W2 and so on. So in that hypothetical stable matching M prime, the possible partner of M double prime, which is not W because W is matched with M prime, can be below W. Do you see? By induction hypothesis M prime in any stable matching can be matched with W or below, but W is matched with M prime. So M double prime is matched with below W. So for we also have then for M double prime prefers W than his partner. Because of induction hypothesis, and that is why this is a blocking pair for M prime. Question, any immediate question? So what I have shown here is that if I run the DA algorithm once, with respect to them I define these sets and all the rejections, there can be no stable matching where these rejected pairs can be matched. Okay. I think this is a good time to break for tea. You think about this, and then if you just have peace of mind, and then you will see that this this gives you that theorem as corollary, everything, output, number of iterations and those sort of things, but we will discuss, do not worry, we will discuss.